Warm welcome to one and all. Introducing myself, my name is Mahesh Iyer, working as a faculty, the Department of Mechanical Engineering, Government Engineering College, Ramnagar. I am going to give a presentation on Bode plots, which is coming under Module 4, prescribed by Visheshwara Technological University for 7th semester Mechanical Engineering students. Now, before dealing with the second problem, or problem number 2, what are all we discussed in the previous presentation. So in the previous presentation, I have explained the concept of Bode plot, what you mean by Bode plot, what are all the individual plots of coming under Bode plot, how to get the value of gain crossover frequency, phase crossover frequency, from gain crossover frequency and phase crossover frequency, how to get the gain margin, then phase margin, then how to predict the stability. Then how to plot the individual plot for different magnitudes, how to show positive magnitude, negative magnitude, how to mark the angles, how to take mark the frequencies, everything I have explained in the previous class or previous presentation. Now I will move on to the presentation 2. In the presentation 2, I have taken another problem where we will come across quadratic pole. Let us consider the problem. For the open loop transfer function given, construct the Bode plot and determine gain margin, phase margin, and comment on stability. Now this is the given problem. G of s into h of s is equals to 242 into s plus 5 divided by s into s plus 1 into s square plus 5s plus 121. So reduce this into time constant form. Wherever it is not in 1 plus ts, reduce into 1 plus ts. So here it is s plus 5, take 5 common, s by 5 plus 1. So here you take, it is anyhow a standard form. So here you take 121, it is s square by 121, 5 by plus 5 by 121 s into 1. Then if you simplify this, so this is the final form of open loop transfer function. So 10 into s by 5 plus 1 divided by s into s plus 1 into 1 plus 0.041s plus s square by 121. Now, whenever you come across quadratic pole, so you should compare this quadratic pole with the second order equation. So, right, 1 by s square plus 2 zeta omega ns plus omega n square. So, this is the second order equation, standard equation. So, compare this quadratic pole with this second order equation. If you compare that, we are going to get 2 zeta omega n is equals to this is in the 2 zeta omega n is equals to 5. Get the value of zeta. Omega n square is equals to 121. Omega n is 11. Then correction factor due to damping is minus 20 log 2 zeta. It is plus 7.13 decibels. Already you have come across the concept of this damping factor. Effect of damping is to reduce the amount of vibration in case of damping. Same thing holds good with reference to the magnitude plot, where it will going to reduce the amount of magnitude. So when for quadratic pole, so that you have to accommodate in the form of correction factor. So step number 2, as usual, identify the factors. You see first any constant is there, so constant is equals to 10. Then second, you see that any pole at the origin or 0 at the origin, in this case one pole at the origin, 1 by s. Then arrange the other poles in the order of ascending order, that is the case. Next comes simple pole, 1 divided by s plus 1. Then another simple 0, s by 5 plus 1. The last one, quadratic pole, 1 divided by so and so. So here for quadratic pole, the crossover frequency or the omega c corner frequency is nothing but natural frequency itself, 11 radians per second. For other poles and zeros, you know how to find the corner frequency. Let us say s by 5 plus 1. Here it is in the form of 1 plus ts. T is equals to 1 by 5. So get the corner frequency of this. So omega, maybe omega c4 is equals to 1 by t4. It is 5. Similarly for this 1, for this 11. So that is the case. In that order I have arranged in the ascending order. So next comes magnitude factor analysis. First you find out the magnitude of the constant. So constant magnitude or magnitude contributed by the constant is given by 20 log base 10 of that constant. 20 log base 10 is 20 decibels. Then next comes one pole at the origin, always at minus 20 decibels. This will continue always the next corner frequency, 1 radians per second. At 1 radians per second, you see what is the contribution. One simple pole, minus 20 decibels. Find out the resultant slope, minus 20, minus 20, minus 40. This will continue next corner frequency, 5 radians per second. So at 5 radians per second, once again a simple 0 is there, that will contribute plus 20. Resultant slope will be minus 40 plus 20 minus 20. This will continue next corner frequency, 11 radians per second. At 11 radians per second, a quadratic pole that will contribute minus 40. Resultant slope will be minus 20 minus 40 minus 60 decibels. Then next comes phase angle plot. Phi is equals to tan inverse of omega by phi minus 90. It is angle of 1 by s minus tan inverse of omega minus tan inverse of 0.04 omega divided by 1 minus omega square 121. How to find out this angle? So whatever you have, that g of s, h of s is so and so. No? In that, replace the value of s by j omega. Then you becomes maybe in the form of a plus ib, imaginary plus real. Then get the value of tan theta, it is imaginary by real. That is the case, it is 1 omega by 5, omega by 1. And here this is the imaginary part, 0.04 by omega into omega divided by 1 minus omega square by 121. So make a table of omega and pi. Omega start with 0.1, 1, 5, 8, 10, 20, infinity. How I have taken this? 0.1 you take initially, then you take 1, next kernel frequency is 5, you can take 4, you can take 9, you can take 10, you can take 15, like that you select. Then find out pi substituting this value. Then after that, you are familiar how to plot the magnitude. You see that what are all the magnitudes contributed by the poles. Here maximum magnitude is 60 decibels. So minus 60 decibels, 20 minus 20 decibels, minus 40 decibels, minus 60 decibels. Now draw a line from 60 up to 1 radians per second, 40 up to 1 radians per second. Similarly, draw a line from 20 plus 20 to 1 radians per second. These are the negative magnitudes. Then you see that magnitude contributed by constant, it is 20 log base 10, it is 20 decibels. Draw a horizontal line. Now we have to draw the resultant magnitude. To draw the resultant magnitude, you see that first magnitude in the magnitude factor analysis, minus 20 decibels. So that minus 20 decibels we have to shift along above that 20 decibels, because I have to draw the resultant magnitude. So you shift this 20 decibels, that is sorry, minus 20 decibels above this 20 decibels constant magnitude. So that will continue till the next corner frequency. Next corner frequency is 1 radians per second. At 1 radians per second, simple pole is there, that will contribute minus 20. Draw minus 40. How to draw minus 40? Keep a scale to this, then draw a line parallel to this. This line is parallel to this minus 40. Then similarly this will continue till 5 radians per second corner frequency. At 5 radians per second, simple 0 is there, resultant magnitude is minus 40 plus 20 minus 20. This will continue next corner frequency 11 radians per second. At 11 radians per second, once again there is a simple pole that will contribute minus 20 minus 20 minus 20, it is minus 40 decibels. So this will continue some infinite distance. So here in this case what happens, so there is a quadratic pole is there, that will reduce the amount of vibration by 7.3 decibels. So show it upwards to positive value. Then at the same time, quadratic pole contribute minus 40 decibels. Remember, quadratic pole contribute minus 40. So minus 20 minus 40 minus 60 decibels. It is not minus 40 decibels, it is minus 60 decibels. So like that. At same 11 radians per second, quadratic pole, effect of zeta is to reduce the amount of magnitude 7.1 upwards. Then mark the angles as usual, 0, minus 60, minus 120, minus 180, like that. Then show these angles. Once if you plot it, you see that wherever magnitude plot crosses 0 decibels, that is omega jc, corresponding to that phase margin, upwards positive. Similarly, this phase angle plot crosses minus 180 degree line. So here corresponding to that omega phase crossover frequency, corresponding to that in the magnitude plot, get the gain margin, it is measured upwards plus 20 decibels. So these are all the values. Gain crossover frequency 2.6 radians per second, phase crossover frequency 11 radians per second, gain margin 20 decibels, phase margin 42 degrees. So after that, since gain margin and phase margin is positive, gain crossover frequency is less than phase crossover frequency, system is completely stable. So what we can conclude from this presentation is, if you know the open loop transfer function, how to reduce it to standard form, how to find the magnitude and phase of the system, how to plot it on semi-log sheet, how to predict the stability of the control system. If we come across quadratic pole, how to get the value of natural frequency, damping factor, how to show the correction of that with reference to damping factor in the magnitude plot. So thank you one and all for your patience listening. So